Constant acceleration formula for a projectile moving in a vertical plane. Now we should remember back from our Mechanics 1 that when we're looking at problems involving a constant acceleration and the motion of a particle, we looked at Subat equations. Now this first section we're going to look at on these two videos is to do with projectiles. And when we're talking about projectiles, we're going to be looking at the Subat equations and using them in the vertical motion, free falling under gravity. And we're also going to look at what is happening in the horizontal plane as well as the vertical plane. Now, when a particle is projected with a speed u at an angle of alpha to the horizontal, it will move along a symmetrical curve. And here we have an example of this. So we've got a particle at the start here, and if we fire it off with a speed of u at an angle of alpha, it will form this nice symmetrical curve where it starts from the ground, horizontal ground, and it's curving round until it hits the ground again. And when we have this situation, we have an initial speed u is referred to as the speed of projection, and the angle alpha represents our angle of projection or angle of elevation. And we can use our diagram here to find out the component of the speed that is acting in the vertical direction and in the horizontal direction. And this is done very similar to how we looked at forces on an incline by looking at it acting perpendicular to the slope and down the slope. Well, it's very similar to that. So we've got our vertical direction, we've got our horizontal direction, and we've got our speed in the middle being projected at u and at a angle of alpha. Now the component of that speed that is acting in the horizontal direction is going to be calculated by doing u cos of alpha. Because if we were to label this triangle that we've got formed here, this side here would be the opposite and this would be the adjacent. Likewise, we can find the component of the speed that is acting vertically upwards, which is going to be u sine of alpha. So we can use this notation, the u and the alpha, to find the component of the speed that is acting vertically and horizontally. Now that's going to be a really important skill to do on every single question involving projectiles, is to firstly find out what the component of the speed is acting vertically and horizontally to the plane. A couple of other key terms that we need to know to do with looking at projectiles. We're going to look at the term greatest height, and this is the greatest height that the particle or the projectile reaches above the horizontal plane. So it's the peak in our symmetrical curve. So this is the greatest height. And when we talk about the range or calculating the range, we're talking about the total distance that is travelled from when the particle is first fired to when it lands. But we're talking about the horizontal distance, not the whole distance around it going up and down. We're talking about the range from where it started to where it ended. We've also got another key thing we could talk about, which is time of flight, which is the time from the first projected to striking the ground again. And in the horizontal plane, the distance is calculated by doing distance equals speed times time. So once we've calculated back here in our diagram the component of the initial speed that is acting horizontally, to find out the range from the start to the end, or the distance, we just need to do the speed times by the time it takes from the moment you fire the projectile to when it hits the ground again, the time of flight. Now, you need to remember those key terms, because when you're tackling a question, you're always going to have those key words and you've got to identify what you're finding from the question. So if we look at an example to do with projectiles on this one, and in the next video we're going to look at a slightly more difficult problem and more like an exam style question. Now, the real key thing to do on all these questions to do with projectiles is to draw your diagram clearly, like you got into the habit of in Mechanics 1. So it says, a particle Q is projected from a point O on a horizontal plane with speed 33 meters per second to the -1. and with an angle of projection of 45 degrees. After projection, the particle moves freely under gravity until it strikes the plane at point B. Find the greatest height reached by Q, the time of flight, and the distance from O to B. Now remember, when a particle is moving freely under gravity, like it is in this question, we use gravity as equal to 9.8 meters per second to the minus 2, which we use a lot of in Mechanics 1 to do with SUVAT problems. Now what we need to do, as I said, is we need to draw our diagram. So our particle, when projected, is going to take a path like this, along a horizontal plane, along the ground, here. Now what we're told is it initially goes off at a angle of 45 degrees, and we have a initial speed or speed of projection of 33 meters per second to the minus 1. Now before we start answering our three parts of our question, I would always write down what component of the speed is acting in the horizontal direction and in the vertical direction. So the horizontal direction is going to be 33 of cos 45, which you could type into a calculator and find the answer to. In some questions that would be appropriate. And in the vertical direction, you're going to do 33 sine of 45 degrees. So now we've got that, we can start tackling our initial question. And the first thing we've asked to do in part 1 is to calculate the greatest height. So this is the height in the middle here, where it's the greatest distance from there to the horizontal plane. And to do that, we're going to use our old friend SUVAT. And as we got into habit in Mechanics 1 of writing down each part we know in SUVAT, we're going to do that again. Now, because we're looking at the greatest height, which is this part here, we're talking about the vertical plane. And the vertical plane, the initial speed we've got is this section here, which is the 33 sine of 45. Now we're trying to find the greatest height, so that is what we are looking for, the S. The final velocity, final speed, well, when we've got our particle at the top here at the greatest height, well, its speed is 0 because it's just stopped. It slowed down until it got to the point, stops there, and it's going to start speeding up again back to the ground. So the U is 0. The acceleration, well, as it's going upwards, it's going against gravity, so it's going to be minus 9.8, and we don't know anything about the time, so we're not going to use that. Now we've got to think back to our Mechanics 1 here. Which SUVAT equation does not have a t in it? Well, that is v squared equals u squared plus 2as. And if we substitute in what we know, well, the v is 0, so 0 squared. Our u is 33 sine of 45 all squared. Now, because it's minus 9.8, I'm going to put minus 2 times 9.8 times by the s. And if we tidy this up a little bit, so it's going to be 0 equals 33 sine of 45 all squared minus 19.6s. The way to solve this is to add the 19.6s to both sides, so 19.6s is equal to 33 sine of 45 squared. And if you type that all into a calculator, you get the answer 27.8 ... Now, because we've only got our initial acceleration to two significant figures, we can only give our answer to two significant figures. So this is going to round up to 28 meters. So the greatest height of this particle reaches is 28 metres. Now we look at section 2. In question 2, we're asked to find the time of flight, which is the time it takes from its initial point to its end point at B. So we didn't label that on our diagram, but let's do that. This was O and this was point B. Now, yet again, we're going to use suvat in our vertical plane. So if we label everything we know, so yet again, the first thing it does is when you project it, it acts against its gravity, so it's minus 9.8 acceleration. We don't know anything about the speed when it hits the ground, so that's the bit we don't know. We're asked to find the time. The initial speed is still the same as what we had before, which is 33 sine of 45. But the difference now is, remember, S stands for the displacement. So in the vertical plane, what is the displacement from where we initially started to when we finished on this horizontal plane? Well, it's 0. So our displacement is 0. This time what we're looking for is a suvat equation that doesn't include the V, which, if we remember back, that is S equals ut plus a half at squared. And if we substitute in what we know, we've got 0 equals the initial, which is 33 sine of 45 times by the time, minus, because it's minus 9.8, a half times 9.8 times t squared. If we sort this out, we've got 0 equals 33 sine of 45t minus 4.9 t squared. Now the easiest way to solve this is, because we've got a negative 4.9 t squared, so add everything onto the left hand side of the equation and set it equal to 0. So that's what I'm going to do. So 4.9 t squared, and then because this part here, the 33 sine of 45t, is positive, we're going to subtract that from both sides, and that is equal to 0. Now you may notice in our two terms here we have a t, so we can take a common factor of t out. So 4.9 t, it's just going to be t now, not t squared, and minus 33 sine of 45 equals 0. Now remember, the only way that you can get 0 and multiplying two numbers together, because that's what we've got here, is when either this is equal to 0 or this part here is equal to 0. So either the time is going to be equal to 0, or the time is equal to, setting this section here equal to 0. So 4.9 t minus 33 sine of 45 equals 0, which, if you rearrange this, you get t equals 33 sine of 45 over 4.9. Type this into a calculator and you get t equal to 4.8 seconds. Yet again, to two significant figures, because that's what we're using. Our acceleration has only got two significant figures. The third part of the question was to calculate the distance from O to B, which is another way of saying calculate the range of this projectile. Now, because it's in the horizontal plane, all we need to do is to do distance equals speed times time, an equation you've been using since GCSE. So we need to use our speed, which is now the horizontal component of our initial 33 meters per second to the minus 1, and then times it by the time we've just found. So part 3, we're going to do distance equals speed times time. So distance equals 33 cos of 45, which is the horizontal component of the speed, times it by 4.8, and we get d is equal to 112 meters, which we're going to have to put as 110 meters because our other two, this value here, was calculated by using the acceleration 9.8. And this is a very standard setup for what you want to do for any question to do with a projectile of a particle.